Welcome to the deep dive. Today, we're not just talking about flying, we're talking about getting somewhere specific in the sky.
Right, how pilots actually map their way across the country using visual flight rules, or VFR.
And we're pulling this straight from the source, the Pilot's Handbook of Aeronautical Knowledge, Chapter 16, a real foundational text.
Yeah, think of this deep dive as kind of unlocking the pilot's toolkit for navigating without relying solely on complex instrument systems.
Yes.
It's really about turning that line on a paper chart into a precise journey through the air.
Combining maps, math,
And a bit of airborne cleverness, yeah.
So our mission to unpack the absolute essentials. We're talking visual navigation, dead reckoning, radio aids.
And how they all fit together, how they give a pilot the confidence to, stay on course safely and efficiently, mile after mile.
It really is fundamental knowledge, isn't it? It underpins pretty much everything else in navigation.
It really does. So let's dig into this material, see what guiding principles pop out.
Okay, so let's start at the beginning. What does the handbook actually mean by air navigation?
Simply put, it's the skill of piloting an aircraft from one geographic point to another. But critically, while always knowing where you are relative to the ground.
Always knowing where you are.
And right away, the source is clear. This absolutely requires planning. Serious planning.
Right, you can't just wing it, huh?
Yeah.
Unintended there. What kind of planning are we talking about before you even, start the engine?
Oh, it's a whole process. First, you're plotting your intended path, your course directly onto a chart, a map.
Okay.
Then you're selecting specific points on the ground you expect to see along the way. Landmarks, towns, rivers.
Things you can spot from the air?
Exactly. Checkpoints. You measure the distances between them, you get the latest weather forecasts. Crucial, figure out how long the flight should take.
Calculate the headings, the directions you need to steer.
And, maybe most critically, calculate precisely how much fuel you'll need, plus reserves.
So it is kind of like planning a road trip, but yeah, in 3 dimensions, and definitely with more math involved.
A fair bit more math, yes.
And the source mentions 3 main techniques pilots use for this kind of VFR navigation.
That's right. First, there's pilotage that's navigating mostly by looking out the window, comparing those landmarks you picked out to what's on your chart.
Okay, makes sense. See it, match it.
Then there's dead reckoning. That relies purely on calculations, directions, speed, time, distance, starting from a known point.
Calculating where you should be.
Exactly. And finally, radio navigation, which uses electronic signals from ground stations or satellites.
And in reality, pilots are usually blending these, right?
Oh, constantly. Using all 3 together gives you the best picture.
Okay, pilotage looking outside, matching the map that seems intuitive, but you need the right map. That brings us to aeronautical charts. These are really the VFR pilot's roadmap for the sky.
They absolutely are. Their main job is to help you keep track of where you are, obviously, but also to provide tons of crucial safety information.
Like what kind of info?
Oh, airports, airspace boundaries and types, navigation aids like VORs, terrain elevations, significant obstructions like towers. Basically everything you need to know about what's below and around you.
And the book talks about different kinds of charts, right? Depending on the flight. The sectional chart seems to be the main one.
By far, that's your standard day-to-day VFR chart. Its scale is 1 to 500,000, which means 1 inch on the chart represents about 6.86 nautical miles, or roughly 8 statute miles on the ground.
Okay, so pretty detailed.
Yeah, that scale allows for a lot of detail. All that airport data, airspace info, roads, rivers, terrain features, understanding the legend, all those symbols is absolutely vital.
And these aren't static maps, are there? They get updated.
Oh yeah, very important. They're generally revised every 6 months in most areas. Things change on the ground, airspace changes. You need current charts.
What about those VFR Terminal Area Charts? When would you use those?
Those are specifically for navigating around really busy major airports, especially those complex Class B airspace areas.
Like around LAX or O'Hare.
Exactly. They have a larger scale, 1 to 250,000.
Right.
So 1 inch is only about 4 statute miles.
Even more detail.
Much more topographical detail, yeah. Really helpful when you need precise visual navigation in a congested terminal area. They're also usually updated semi-annually.
And for longer flights, maybe covering bigger distances faster.
Then you might use the World Aeronautical Chart, or WAC chart. The scale is much smaller, 1 to 1,000,000. 1 inch is almost 16 statute miles.
So less detail.
Less detail, yes, but they cover huge areas. Good for moderate speed aircraft on longer cross countries where you don't need the super fine detail of a sectional every minute. They're revised annually or sometimes biennially.
So you pick the chart that fits the mission, and finding out which charts you need is easy.
Yep, the FAA's website, airnav.faa.gov, has a free catalog of all the official charts. Easy to find what you need.
All right, so you've got your chart, your roadmap. Now the next step is figuring out how to pinpoint exactly where you are on that map and which direction to fly. This gets us into the Earth's grid system, latitude and longitude.
Yeah, this is fundamental stuff. High school geography, but absolutely critical for aviation. Latitude lines, called parallels, run east-west, parallel to the equator.
Measuring north or south.
Right. They measure your distance north or south from the equator, which is 0 degrees latitude, all the way up to 90 degrees north or south at the poles. The continental U.S. sits roughly between 25 and 49 degrees north latitude.
And longitude, the up and down line.
Those are the meridians, yeah. They run north-south from pole to pole, kind of like segments of an orange. They measure your distance east or west from the prime meridian.
The 0 degree line through Greenwich, England.
That's the one. The continental U.S. is between about 67 and 125 degrees west longitude.
So any single point on Earth has a unique address, a unique lat-long coordinate.
Precisely. The handbook gives examples, like Washington, D.C. is roughly 39 north, 77 west. Chicago, around 42 north, 88 west. It's the global addressing system.
And those lines of longitude are directly linked to how we measure time across the planet time zones.
They are, yeah. The Earth spins 360 degrees in 24 hours.
Yeah.
You divide that out, it's 15 degrees of longitude per hour of rotation.
So time zones are generally about 15 degrees wide.
That's the standard idea, yeah. About 15 degrees wide, with a 1-hour time difference as you cross from one zone to the next.
Yeah.
Though the actual boundaries get pretty irregular on land for political reasons.
Which is a big deal for pilots, right? Especially flying east.
Oh, absolutely. If you're flying eastward, you're essentially catching up to the sun, flying into later time zones, so you lose time as you cross each zone boundary.
Which matters for calculating arrival time.
Critically important for knowing, say, how much daylight you'll have left when you arrive, relative to sunset at your destination.
And aviation uses a standard time reference to avoid all this confusion.
Yes, thankfully. We use the 24-hour clock format and a single worldwide reference time called Universal Coordinated Time, UTC.
Or Zulu time, as pilots usually call it.
Zulu time, exactly. It's the time at the prime meridian, 0 degrees longitude, all flight plans, weather reports, ATC communication. It's all based on Zulu time.
So you have to convert your local time to Zulu.
Right.
How does that work in the U.S.?
In the contiguous U.S., during standard time, Eastern is Zulu minus 5 hours, Central is Zulu minus 6, Mountain minus 7, and Pacific is Zulu minus 8.
And remember daylight saving time.
Right. You have to subtract 1 less hour during daylight saving time. So Eastern daylight time is Zulu minus 4, for example. Got to keep track of that.
Got it. Okay, so you know where you are on the grid, you know the standard time. Now, how do you figure out precisely which way to point the airplane? This involves measuring direction.
Right. On your aeronautical chart, direction is measured relative to true north, the geographic North Pole, using those meridians of longitude as reference lines.
And it's measured in degrees.
Measured in degrees, clockwise from true north. From 0 up to 360 degrees, 360 is north, 090 is east, 180 is south, 270 is west.
So the line you actually draw on your chart from where you start to where you're going, that's your true course, or TC.
Yes, exactly. That line represents the intended path you want the aircraft to follow over the ground. Its direction, measured clockwise from true north, is your true course.
And the handbook mentions measuring it near the midpoint of the line.
Yeah, that's because the longitude lines converge slightly towards the poles. Measuring near the middle gives you the best average direction for the whole leg. So a TC of, say, 065 degrees is roughly northeast. The reciprocal course, the way back, would be 180 degrees different, so 245 degrees.
But the direction the airplane's nose is pointing isn't always the same as that true course line on the map, especially if there's wind, right? That's true heading.
Precisely. True heading, or TH, is the direction the longitudinal axis of the aircraft the nose is actually pointing, also measured clockwise from true north.
So if there's no wind,
in perfectly still air, yes, your true heading would be the same as your true course to make the aircraft follow that line. But as soon as there's wind,
which there almost always is.
Yeah, almost always. You have to point the aircraft slightly into the wind to counteract its drift, so that your actual path over the ground matches your desired true course.
Okay, that makes sense. Now, this brings us to a really fundamental concept for pilots. The difference between true north and magnetic north. The compass in the cockpit doesn't point to true north, does it?
No, it absolutely does not. This is critical. Your magnetic compass points towards the Earth's magnetic north pole, which is actually a constant shifting point up in the Canadian Arctic, hundreds of miles away from the geographic North Pole, true north.
So there's an angle between the two.
Yes, and that angle, the difference between the direction to true north and the direction to magnetic north at your specific location on Earth, is called magnetic variation.
And that angle changes depending on where you are.
Significantly. It varies all over the globe. On aeronautical charts, this variation is shown by dashed magenta lines called isogonic lines.
ISO what?
Isogonic. They connect points on the Earth that have the same magnetic variation. There's also one special line called the agonic line, where the variation is 0. True north and magnetic north happen to align from that location.
Where is that agonic line roughly in the U.S.?
According to the source, it runs sort of irregularly, but roughly west of the Great Lakes, down south through Wisconsin, Illinois, western Tennessee, and then near the border of Mississippi and Alabama.
So what's the general trend for variation in the U.S.?
Generally, if you're east of that agonic line, say on the East Coast, magnetic north is west of true north, so you have westerly variation. If you're west of the agonic line on the West Coast, magnetic north is east of true north, giving you easterly variation.
Okay, so because your compass points to magnetic north, but your course is drawn relative to true north, you have to convert between them.
You absolutely must. Your true course, that line on the chart, needs to be converted into a magnetic direction before you can use it with your compass.
How do you do that conversion?
You look at the nearest isogonic line on your chart for the amount of variation and whether it's east or west. Then you apply a simple rule to convert from true to magnetic.
Is there a mnemonic for that?
There is. The classic one is east is least, west is best.
East is least, west is best.
Meaning, if you have easterly variation, you subtract it from your true course or true heading to get the magnetic value. East is least. If you have westerly variation, you add it. West is best.
Okay, let's try that. Say your true course is 360 degrees due north, and the chart shows the variation is 9 degrees east.
Okay, 9 east. East is least, so you subtract. 360 minus 9 equals 351 degrees. That's your magnetic course.
What if the true course was 090 degrees due east, and the variation was still 9 degrees east?
Same rule. East is least. Subtract 9 from 090. Your magnetic course is 081 degrees.
Got it. So that gives you the magnetic course or magnetic heading. But wait, there's another correction needed for the compass.
Yes, one more step to get to what the compass actually reads. Even after accounting for variation, the magnetic compass inside your specific aircraft might not point exactly to magnetic north. There's local interference.
Interference from what?
It's called magnetic deviation. It's caused by magnetic fields generated within the aircraft itself, things like electrical wiring, radios, the engine's metal parts, even steel components in the airframe.
And this is unique to each plane.
Absolutely unique to each individual aircraft. It can even change slightly depending on which direction the aircraft is heading and what electrical equipment is turned on.
So how on earth do you account for that?
Every aircraft has to have a compass deviation card mounted right near the magnetic compass. This card is created during a maintenance procedure called swinging the compass.
Swinging the compass.
Yeah, they basically align the aircraft on known magnetic headings on the ground, usually using a calibrated compass rose painted on the ramp, and they record the difference between the known magnetic heading and what the aircraft's compass actually reads on each heading.
And the card shows those differences.
Exactly. The deviation card lists the correction, how many degrees to add or subtract for various magnetic headings, usually in 30-degree increments. You look up the correction for your intended magnetic heading and apply it.
Okay, so let's recap the whole conversion chain to get from the line on the chart to the number you steer on the compass.
It's a sequence. You start with your true course, TC from the chart. You apply the wind correction angle, WCA, to get your true heading, TH.
TC plus or minus WCA gives TH.
Then you apply magnetic variation, V, using east is least, west is best, to get magnetic heading, MH.
TH plus or minus V gives MH.
Finally, you apply the correction for magnetic deviation, D, from the compass card to get your compass heading, CH.
MH plus or minus D gives CH. That's the number you actually fly by reference to the compass.
That's the full sequence. TCA, WCA, VCA, VVV equals MH, WCA equals CH. We've covered V and D. Now we need to talk about that WCA, the wind correction angle.
Ah, yes, the wind, the invisible hand that messes everything up sometimes.
It certainly keeps things interesting. Fundamentally, wind is just air moving across the surface of the Earth. Your aircraft flies through that mass of air.
So if the air itself is moving...
Then it carries the aircraft along with it relative to the ground.
Okay, so your airspeed, how fast you're moving through the air mass, that's not affected by wind?
Correct. Your indicated airspeed, or true airspeed, is independent of the wind. But your ground speed, how fast you're actually moving over the ground, is definitely affected.
How so?
A tailwind, wind blowing from behind you, increases your ground speed, makes you faster over the ground than your airspeed. A headwind blowing against you decreases your ground speed. And a crosswind
Blows you sideways.
Exactly. A crosswind pushes you off your intended track if you don't correct for it.
The book is an example. 120 knots airspeed plus a 20-knot tailwind equals 140 knots ground speed.
Perfect example. Simple addition or subtraction if the wind is directly on your nose or tail.
But if it's a crosswind, it affects your path over the ground, your track.
Right. Your heading, the direction the nose is pointing, won't be the same as your track, the actual path you're making over the ground. That difference is called the drift angle.
So to make your track match your desired course line on the chart, you have to point the nose into the wind somewhat.
Precisely. And that angle you crab into the wind, the difference between your desired course and the heading you need to fly, is the wind correction angle, or WCA.
If the wind's coming from your left, you aim the nose a bit to the left of your course.
Exactly. You calculate that WCA and also your expected ground speed during your pre-flight planning. You use tools like a flight computer, the old E6B whiz wheel, or an electronic calculator using the forecast winds aloft for your altitude and your planned true airspeed.
Wow, it sounds like a lot of interconnected calculations just to figure out which way to point and how fast you'll get there.
It is, but it all boils down to some fundamental relationships. Basic math for time, speed, distance, and of course, fuel. These calculations are absolutely non-negotiable before any cross-country flight.
Okay, let's hit the basics. Time equals
distance divided by ground speed. T equals dGGS.
So if a leg of your flight is 210 nautical miles and you calculated your ground speed with the wind will be 140 knots.
Then the time for that leg is 210 divided by 140, which is 1.5 hours, or 1 hour and 30 minutes.
Okay. Distance equals?
Distance equals ground speed multiplied by time. D equals GSXT.
So if you fly for, say, 1 hour and 45 minutes, that's 1.75 hours at a ground speed of 120 knots.
Then you'll cover 120 times 1.75, which equals 210 nautical miles.
So finally, ground speed equals?
Ground speed equals distance divided by time. GS equals DT.
So if you flew 270 nautical miles and it took you exactly 3 hours.
Your average ground speed was 270 divided by 3, which is 90 knots. Simple formulas, but absolutely vital for planning and for checking your progress in flight.
And what about fuel? Arguably the most important calculation.
Couldn't agree more. This is critical. Most piston aircraft measure fuel burn in gallons per hour, GPH. Turbine aircraft usually use pounds per hour.
So how do you figure out how much fuel a trip will take?
You multiply your total estimated flight time by your aircraft's specific fuel burn rate at your planned power setting and altitude.
For example, a 4-hour flight at 5 GPH
Needs 4 times 5, which is 20 gallons of fuel, but that's just for the flight itself.
Right. You need reserves.
Always.
Yeah.
Legally required reserves, plus maybe a personal minimum on top of that.
And the key here is using the flight time based on ground speed, right? Because that determines how long you're actually airborne.
Exactly. Your engine burns fuel at a relatively constant rate for a given power setting. But how long you burn that fuel depends entirely on how long it takes you to cover the distance over the ground, which depends on your ground speed.
Makes sense. The faster your ground speed, the less time you fly, the less total fuel you burn for that distance.
Precisely. The source also mentions thinking about specific range like nautical miles per gallon, which automatically incorporates the effect of wind on your efficiency.
And you always plan for more fuel than the bare minimum calculation shows.
Absolutely. Factor in extra fuel for engine start, taxi, the climb phase where you burn more fuel and have a lower ground speed, and then add your required reserve fuel, plus maybe a safety buffer.
And the cardinal rule.
Plan to land with fuel still in the tanks, well before the gauges read empty or you hit your calculated minimum fuel. Your aircraft's flight manual, the AFM or POH, has all the specific charts for fuel consumption at different altitudes and power settings.
Okay, so you've done the basic calculations, you understand the concepts. How do you pull all this together into a solid pre-flight plan? The regulations, 14 CFR Part 91, say the pilot in command must be familiar with all available information.
That's the rule. And all available information means a lot. It means knowing the weather forecasts and reports, checking your fuel requirements, including reserves, planning for potential alternate airports if your destination is forecast to be iffy, and being aware of any known ATC delays or potential hazards along your route.
So, what are the essential tools and materials you need laid out on the table?
You definitely need your current aeronautical charts, sectionals, probably for the entire route, and the areas around any potential alternate airports. You need your flight computer, whether it's the classic E6B whiz wheel or an electronic one.
A plotter.
A plotter, yes, to measure distances and course lines accurately on the chart. And any necessary survival gear depending on the flight, maybe a flashlight for night flying, extra water if you're flying over remote desert areas.
And checking the weather is step one.
Often, yes, check it early. The weather might completely change your plans, dictate your route, your altitude, or even tell you it's not safe to go at all. That's a whole separate deep dive on aviation weather services.
You also need specific info about the airport's departure, destination, and alternates. Where does that come from?
That primary source is the Chart Supplement US. It used to be called the Airport Facility Directory, or AFD.
What's in there?
It's packed with vital details for every public use airport. Its exact location, elevation, runway lengths, widths, surfaces, lighting systems, available services like fuel types and repairs, radio frequencies for towers, ground control, Unicom, flight service stations, details about the traffic pattern, hours of operation, and really important remarks about noise abatement or local hazards. It also has info on nav aids.
But things can change quickly. What about temporary changes not in the printed chart supplement?
That's where NOTAMs come in, notices to airmen. These are time-critical updates issued between publication cycles that cover things like temporary runway closures, construction, inoperative lights or nav aids, temporary flight restrictions. Anything hazardous or different from what's published, you must check NOTAMs before every flight.
So chart supplement for the baseline info, NOTAMs for the latest updates.
Exactly. The sectional chart itself also has a small bulletin section for major changes since it was printed. But the chart supplement and NOTAMs are generally more current for airport specifics.
And finally, you need information specific to the actual airplane you'll be flying.
Yes, back to the AFM or POH for that specific aircraft. Two absolutely critical checks here: weight and balance and performance.
Weight and balance.
You have to calculate the aircraft's total weight, the empty weight plus fuel, oil, passengers, baggage, and ensure it doesn't exceed the maximum allowable gross weight. Just as importantly, you have to calculate where the center of gravity, CG, is located and make sure it's within the approved forward and aft limits.
Why is that so critical?
An overloaded aircraft won't perform as expected, and an aircraft with the CG outside the limits can be unstable or even uncontrollable. It's a fundamental safety check. Use the latest weight and balance data for that specific serial number aircraft.
And performance calculations.
Using the charts in the POH, you determine the expected takeoff distance and landing distance based on your calculated weight, the airport's elevation, and the forecast temperature and wind. Then you compare those distances to the actual runway lengths available at your departure and destination airports.
And remember the factors that affect performance.
Absolutely. Heavier weight, higher airport elevation, hotter temperatures, less headwind, all these things increase your takeoff and landing distances and decrease your climb rate. You have to ensure you have enough performance for the conditions. And as we said, check the fuel burn charts and calculate your total fuel needed, including reserves.
Wow. It really is a comprehensive process before you even get near the plane. Let's try to walk through putting this on the chart using the example from the handbook. Flying from Chickasha Municipal to Guthrie-Edmond Regional in Oklahoma.
Okay, yeah, the source uses that as a good practical example. The first physical step is just drawing a straight line on your sectional chart, connecting the center of the departure airport symbol, Chickasha, to the center of the destination airport symbol, Guthrie.
Simple enough. Then you pick checkpoints along that line.
Yes, you look along that course line and identify prominent features on the chart that you expect to be able to see easily from the air.
Like what?
The source suggests things like large towns, often marked in yellow on the chart, distinctive lakes or rivers, major highways or railroad tracks that cross your path. Sometimes using features parallel to your course can act as brackets to keep you from straying too far left or right.
Any pitfalls with choosing checkpoints?
Yeah. A couple of important ones. First, never rely on just a single checkpoint for a leg. Always have a sequence. Second, remember that charts have a publication date. Features on the ground might have changed. A road might be new, a building torn down. Use prominent, lasting features.
What about tall towers or antennas? They can pop up quickly.
Very important point. Charts show tall obstructions, but new ones might exist. Always check the maximum elevation figures, MEFs, shown in each quadrangle on the chart and plan to fly well above the highest terrain or obstruction in your area. The source specifically mentions staying at least 500 feet, preferably more, above the tallest known obstruction near your route.
And a key safety tip if you get disoriented.
If you're ever unsure of your position, the best initial action is often just to hold your current heading steady. Don't start making random turns hoping to spot something. Maintain heading, try to reorient using other methods.
Okay, while you're drawing the line and picking checkpoints, you're also carefully checking the airspace and terrain along that route.
Absolutely crucial. You need to identify any controlled airspace your route might penetrate or come close to. In the Chickasha-Guthrie example, the flight path goes near Oklahoma City's Class C airspace and Wiley Post Class D. You need to know the vertical limits, floors and ceilings, and the operating rules for that airspace.
And terrain.
Same thing. Identify the highest terrain elevations and the tallest charted obstructions along and near your route. The example notes a 2,749-foot antenna and general terrain up to 2,900 feet MSL along that path.
Which directly influences your choice of cruising altitude.
Right. You need to pick an altitude that provides safe clearance over all terrain and obstructions, complies with airspace requirements, and also considers factors like winds aloft, cloud layers, and aircraft performance.
And there's that VFR cruising altitude rule.
Yes. For flights above 3,000 feet above the ground, AGL, on a magnetic course between 0 and 179 degrees, you fly at an ODD 1,000-foot MSL altitude plus 500 feet, like 3,500, 5,500, 7,500. For magnetic courses 180 through 359 degrees, you fly at an even 1,000 plus 500 feet, like 4,500, 6,500, 8,500.
So for the Chickasha-Guthrie example, which has an easterly course, they chose
5,500 feet MSL. That's an odd plus 500 altitude, appropriate for their magnetic course, and it provides good clearance over the terrain and known obstructions, and keeps them clear of the overlying Class C airspace in that area.
Okay, altitude selected. Next, measure the distances.
Yep, use your plotter to measure the total distance of the course line. The example flight is 53 nautical miles. And critically, measure the distance between each of those checkpoints you selected. You'll use those segment distances later.
And then measure the direction of that line, the true course.
Using the plotter again, aligning it with the meridian near the midpoint, you measure the true course. For Chickasha to Guthrie, the example gets 031 degrees true course.
All right, now the big calculation moment. Finding the headings, using that formula, TC Hamani I WCA equals THV equals MH Manny D equals CH.
Okay, let's walk through it for the example. TC is 031 degrees.
First, WCA wind correction angle.
You need the forecast winds aloft for your altitude, 5,500 feet.
Yeah.
The example uses wind from 360 degrees at 10 knots. You also need your planned true airspeed, TAS. They use 115 knots. Plug those into your flight computer.
And it calculates the WCA. The example result is 3 degrees left.
Okay, so to correct for that wind from the north, slightly left, you need to steer 3 degrees left. True course 031 minus 3 degrees WCA equals true heading, TH 028 degrees.
Next step, apply variation, V.
Look on the chart near your route for the nearest isogonic line. The example finds one indicating about 7 degrees east variation.
Apply the rule, east is least.
So you subtract the east variation. True heading 028 minus 7 degrees east variation equals magnetic heading, MH 021 degrees.
Last step, apply deviation D.
You look at the deviation card next to the compass in that specific aircraft. The example assumes the card shows a plus 2 degree correction is needed when flying on a magnetic heading near 021.
So add 2 degrees.
Magnetic heading 021 plus 2 degrees deviation equals compass heading, CH, 023 degrees. That's the actual number you'll try to keep the compass needle on while flying that leg, assuming the wind forecast is accurate.
And that same wind calculation on the flight computer also gives you your expected ground speed, GS.
Yes. With the 10-knot headwind component from the north wind, the example calculates a ground speed of 106 knots, slower than their 115 knots TAS.
Now you can calculate time and fuel for the leg.
Right. Estimated time en route, ETE, is total distance divided by ground speed. 53 nautical miles divided by 106 knots equals 0.5 hours, which is 30 minutes.
But you need to add time for the climb.
Good point. You estimate how long the climb to 5,500 feet will take, maybe 5 minutes in this light aircraft example. So total ETE is 30 plus 5 equals 35 minutes.
And fuel burn?
Multiply that total time in hours. 35 minutes is about 0.58 hours. By the aircraft's fuel burn rate from the POH, say it's 8 gallons per hour. 0.58 times 8 equals about 4.7 gallons needed for this leg, not including taxi or reserves.
And you meticulously record all of this planned information on a flight log.
Exactly. The source shows a sample visual flight log. You write down each checkpoint, the distances between them, the calculated headings, true, magnetic, compass, estimated times for each leg and cumulative time, and planned fuel burn.
And then you use that log in flight.
Yes, as you fly over each checkpoint, you note the actual time. You can then compare your actual time between checkpoints to your estimated time, calculate your actual ground speed, and update your estimates for the remaining legs and your fuel situation. It's a dynamic process.
So that really demonstrates how you blend the chart work, pilotage planning, the calculations, dead reckoning, and the visual checkpoints, pilotage execution. Now, what about filing a VFR flight plan? The source says it's not legally required for VFR flights, but highly recommended. Why?
It's purely a safety measure, but a really important one. Filing a VFR flight plan essentially tells the FAA's flight service system your intended route, destination, estimated time and route, number of people on board, etc.
So if you don't show up.
If you don't close your flight plan by contacting flight service within a certain time after your estimated arrival, they initiate search and rescue procedures. It's like telling someone where you're hiking and when you expect to be back. It provides a safety net if something goes wrong and you can't communicate.
How do you actually file one?
The easiest way is usually to call flight service on the phone before you depart. You give them all the information for the flight plan form.
But filing it isn't enough, right? You have to activate it.
Crucial step. Once you're airborne and clear of the airport traffic pattern, you contact flight service again, usually on the radio, and tell them you want to activate your VFR flight plan. Only then is it live in their system.
And the source mentions a potential pitfall here.
Yes, a really important one. If you file by phone, flight service will only hold on to your proposed flight plan for 1 hour past your proposed departure time. If they don't hear from you within that hour, either activating it, giving them your actual departure time, or giving them a revised departure time, they automatically cancel the flight plan. And they often don't explicitly tell you that rule.
So if you get delayed on the ground for more than an hour,
you need to call them back with an updated time, or your safety net disappears without you necessarily knowing it.
The source shows the standard flight plan form. Any key fields we should highlight for VFR pilots?
Yeah, a few points. Item 3 is aircraft type and special equipment. You use standard codes, like maybe C172G for a Cessna 172 with GPS. The codes are in the Aeronautical Information Manual, AMM.
Item 6, departure time.
That's your proposed departure time, and it must be in UTC, or Zulu time.
Item 7, cruising altitude.
For VSR, you can actually just write VFR in this block, since you'll choose your specific altitude based on the cruising altitude rules, weather, and terrain, just indicating VFR is acceptable.
Item 8, rate of flight.
You can write direct if you're flying a straight line, or you can list specific VORs, waypoints, or towns you plan to navigate via.
Item 10, estimated time en route.
This should be your total calculated time from takeoff to landing, including the estimated time for your climb phase.
And item 12, fuel on board.
This is important. It's not the number of gallons, but the total time your fuel will last, expressed in hours and minutes. You calculate this by dividing your total usable fuel quantity by your planned hourly fuel consumption rate.
And the absolute final step after landing safely.
Close your flight plan. Call flight service. Tell them you've arrived safely at your destination. Forgetting this triggers those unnecessary search and rescue efforts. Phoning them is usually the most reliable way to close it.
Okay, excellent. We've covered using charts, calculations, planning. Now, the third main navigation method mentioned is radio navigation. The source calls it a supplement for VFR pilots.
It really is. It adds another layer of precision and safety, especially when visual landmarks aren't clear or you're over unfamiliar terrain or maybe visibility isn't perfect. It helps you stay oriented.
And the three main systems discussed are VOR, NDB, and GPS.
That's right. Those are the workhorses.
Let's start with VOR, VHF omnidirectional range. What is that?
VORs are ground-based radio stations. They transmit VHF signals outwards in all 360 degrees. You can think of these signals as electronic spokes radiating out from the station hub. Each spoke is called a radial, and it's identified by its magnetic bearing from the station, 001 to 360.
And VHF means line of sight.
Exactly. VHF signals don't bend much around the curvature of the Earth or terrain, so your ability to receive a VOR signal depends on your altitude and whether there's anything physically blocking the path between your aircraft and the station, like a mountain.
Higher altitude generally means longer reception range.
Generally, yes. The Handbook shows a chart illustrating this. There are different classes of VORs, terminal T, low altitude L, and high altitude H, which have different standard service volumes or guaranteed reception ranges, but they're all ultimately limited by line of sight.
How accurate are VORs?
They're quite accurate, typically within plus or minus 1 degree. But pilots need to periodically check the accuracy of their aircraft's VOR receiver using published test signals, VOTs, or ground airborne checkpoints.
And you need to make sure you're tuned to the right station.
Absolutely. Every VOR transmits its own unique identifier, either a 3-letter Morse code sequence or sometimes a recorded voice saying the station name, Oklahoma City VOR, for example. You must listen and positively identify the station before using it for navigation. If you don't hear the ID, assume the station is unreliable or out of service.
What instruments in the cockpit display VOR information?
The most common are the CDI, which stands for Course Deviation Indicator, and the HSI, the Horizontal Situation Indicator. Some older aircraft might have an RMI, a radiomagnetic indicator.
Let's break down the CDI first. What does it show?
Okay, the basic VOR CDI usually has a knob called the OBS, or Omni Bearing Selector. You use this to select a specific VOR radial or course you want to track. There's a vertical needle that swings left or right to show your aircraft's position relative to that selected course. And there's a tow from indicator, usually a little flag or arrow.
How do you use it to find, say, the course to do the station?
You tune and identify the VOR station. Then you rotate the OBS knob until that vertical needle centers, and the indicator shows 20. The course selected on the OBS dial is now the magnetic course you need to fly to get to the station from your current position.
And if the indicator shows from?
If the needle centers with the from indication, the course selected on the OBS is the magnetic radial you are currently on, radiating from the station. The needle always tells you which side of the selected course line you are on. If the needle is to the left, your desired course is to the left.
Got it. Now, the HSI, how is that different?
The HSI is a more advanced display. It basically combines the directional information of a heading indicator, your magnetic compass heading, with the VRLOC navigation information onto one instrument face.
So it shows your heading and the VOR course together?
Exactly. It typically has a little airplane symbol fixed in the center representing your aircraft. The compass card rotates behind it to show your current magnetic heading under the top index. Then there's a course deviation bar, like the CDI needle, that moves left or right relative to the aircraft symbol to show your position relative to the course you've selected with a course pointer or arrow. You also have a tow from indicator.
What's the advantage of an HSI?
It gives you a much better pictorial representation of your situation where you are relative to the desired course and what your heading is. It makes intercepting and tracking courses more intuitive for many pilots. Also, the deviation display on an HSI is often linear scaling, meaning the deflection represents actual distance off course, unlike the angular deflection of a basic CDI needle, which gets more sensitive closer to the station.
And briefly, the RMI.
The radiomagnetic indicator is simpler in concept, though less common now. It has a rotating compass card that shows your magnetic heading, just like an HSI. But instead of a course selector and deviation bar, it has one or more needles that simply point directly towards the tuned VOR or NDB station.
So the RMI needle always shows the magnetic bearing to the station.
That's right. You don't select a course on it. You just read the bearing off the compass card where the needle is pointing.
Okay, so using a standard CDI, how do you actually track a specific VOR radial or inbound course, especially with wind blowing you off course?
It's an active process. First, you tune, identify, and select the desired course on the OBS. Let's say you want to fly TO the station on the 09A course. You turn the aircraft to a heading of roughly 090. Now watch the needle. If it starts drifting off center to the right, it means the wind is pushing you left, of course.
So you need to turn right to get back on course.
Yes, but not just point the needle back to the center. You need to turn towards the needle to re-intercept the course. Maybe turn to a heading of 100 or 110 degrees. Once the needle starts coming back towards the center, you start turning back towards your original desired course. But this time, add a correction into the wind.
Ah, the wind correction angle.
Exactly. If the wind was from your left, pushing you right, you might need to fly a heading of, say, 085 degrees instead of 090 to keep the needle centered once you're back on course. It often takes a bit of bracketing small heading adjustments to find the exact heading that keeps the needle perfectly centered. That heading is your magnetic heading required to track that course over the ground.
What happens when you fly directly over the VOR station?
As you get very close, the needle becomes very sensitive and may swing back and forth erratically. This is called the cone of confusion. Right over the station, the to from flag will flip from a to indication to a from indication. Sometimes an off flag might flicker briefly too.
And if you don't fly exactly over it?
If you pass slightly to one side, the needle will just swing fully to the side the station is on after you pass the point to beam it, and the flag will flip to from.
The source also mentions using the VOR for time and distance checks without DME. How does that work?
Yeah, there are a couple of classic techniques described. One involves timing how long it takes to fly across a specific number of radials when you're flying perpendicular to the course to the station. By knowing your true airspeed and the time taken to cross, say, 10 degrees of radials, you can use some simple trigonometry formulas provided in the handbook to estimate your distance from the station.
Kind of a clever geometric trick.
It is. Requires careful flying and timing, but it works. There's a similar method using an RMI by timing a bearing change. There are ways to get an estimate when you don't have DME.
Speaking of which, DME, distance measuring equipment, that gives you distance directly.
Yeah, DME is a separate system, usually co-located with a VOR, making it a VORTAC, or sometimes with an ILS. It operates on UHF frequencies and provides a direct readout of your distance from the DME ground station in nautical miles.
But it measures slant range, not ground distance.
That's a key point. It measures the direct line-of-sight distance between the aircraft antenna and the ground station antenna. So if you're flying at 6,000 feet, about 1 nm, directly over the station, the DME will read approximately 1.0 nm, even though your distance over the ground is 0. The error is smaller the further away you are.
But still, very useful for knowing your position.
Extremely useful. Having a VOR radial and a DME distance gives you a very precise position fix. Many DME units can also calculate your ground speed and time to station based on the rate of change at the distance.
Is that ground speed accurate?
It's only truly accurate when you're flying directly to or directly from the station. If you're flying at an angle, the slant range geometry makes the calculated ground speed inaccurate. It also takes a few minutes of stable flight towards or away from the station for the ground speed calculation to become reliable.
Okay, so VOR gives you bearing, DME gives you distance. What about VOR dem RNAV, area navigation?
RNAV is a big step up. It's not a ground station itself, but rather an aircraft computer system that uses signals from VORs and DMEs to allow you to navigate along any desired course, not just directly to or from a station.
So you can fly straight lines between any 2 points you define.
Exactly. You define waypoints electronically, usually by specifying a radial and distance from a known VORTAC. The RNAV computer then calculates the course between these waypoints and provides steering guidance on your CDI or HSI, making it seem like there's a VOR right on your desired track.
Does the display look different in RNAV mode?
Often, yes. As we mentioned with HSIs, RNAV systems typically provide linear course deviation information. This means the needle or bar deflection corresponds to a specific distance off course. e.g., full scale might be 5 nm off course in en route mode, or maybe only 1.25 nm in approach mode, rather than an angular deviation that gets more sensitive near a VOR.
And the source notes that approach mode sensitivity isn't really suitable for VFR cross-country.
Right, that high sensitivity is designed for instrument approaches. For VFR navigation between points miles apart, the en route sensitivity is more practical. You need to understand the modes and how the display works for your specific RNAV unit. Reading the manual is essential.
Okay, moving on from viewer DLME-based systems, let's talk about the ADF Automatic Direction Finder. What does that use?
The ADF system in the aircraft tunes into ground stations called NDBs, or non-directional radio beacons. These transmit on much lower frequencies than VORs, typically in the medium frequency MS or low frequency LF bands, around 200 to 415 kilohertz. Some ADFs can even tune into commercial AM radio broadcast stations.
What's a key difference or advantage of using these lower frequency NDB signals?
The big one is that these lower frequency radio waves tend to follow the curvature of the Earth much better than line-of-sight VHF signals.
So not line-of-sight limited.
Correct. You can often receive NDB signals from much further away, especially over water, and at lower altitudes where terrain might block a VOR signal.
Sounds great. What are the downsides?
NDB signals are much more susceptible to various forms of interference. Electrical disturbances like thunderstorms can cause the ADF needle to point towards the lightning instead of the station. Precipitation static, flying through rain or snow, can cause interference. Signals can also bend near coastlines, coastal refraction, or mountains, leading to bearing errors. Accuracy isn't as good as VOR.
How does the ADF instrument itself display the information?
The most common type has a needle that simply points towards the tuned NDB station. This needle is usually superimposed over a compass card. On a basic fixed card, ADF, the card is fixed with 0 degrees representing the nose of the aircraft.
So the needle shows the direction to the station relative to the aircraft's nose.
Exactly. That angle between the aircraft's nose,
Yeah.
0 degrees on the fixed card, and the direction the needle points is called the relative bearing, RB.
If the needle points straight ahead to 0 degrees,
The station is directly in front of you. If it points to 90 degrees, the station is directly off your right wing. If it points to 180 degrees, it's directly behind you.
so how do you get the actual magnetic bearing to the station?
You have to use a simple formula. Magnetic heading, MH, plus relative bearing, RB, equals magnetic bearing, MB, to the station. MH plus RB equals MB.
Okay, MH plus RB equals MB. The source talks about homing versus tracking with an ADF. What's the difference?
This is a really important distinction for using ADF effectively. Homing is the simple technique of just keeping the ADF needle pointed directly at 0 degrees relative bearing, keeping the nose pointed right at the station.
Sounds easy enough. What's wrong with that?
If there's any crosswind, homing will result in you flying a curved path to the station. You'll constantly be turning slightly into the wind to keep the needle on 0, making your actual track over the ground a curve, which is inefficient and takes longer.
So what's tracking?
Tracking involves calculating and flying a specific magnetic heading that accounts for the wind drift, allowing you to maintain a straight-line track, magnetic bearing, over the ground towards the station.
How does the ADF help with tracking?
When you're tracking correctly in a crosswind, the ADF needle will not be on 0 degrees relative bearing. The angle between the needle and 0 will actually show you the wind correction angle you are currently holding relative to the direct bearing to the station. It takes practice to establish the correct heading to maintain that straight track.
Okay, so tracking is more precise and efficient than just homing. Now, finally, let's talk about the navigation system that has become ubiquitous. GPS, the Global Positioning System.
Yes, GPS. It's a satellite-based RNAV system originally developed by the U.S. Department of Defense, but now providing worldwide positioning and navigation capabilities to everyone. It's really revolutionized navigation, especially with portable handheld units becoming so common and capable.
How does it determine your position?
The GPS receiver in your aircraft listens for signals from multiple GPS satellites orbiting the Earth. By calculating the time it takes for signals from different satellites to arrive, the receiver can trilaterate, really its position very accurately.
How many satellites does it need?
To get a basic 3D position, fix latitude, longitude, and altitude, the receiver needs to see signals from a minimum of 4 satellites simultaneously.
And the handbook mentions RAIM. What is that and why is it important?
RAIM stands for Receiver Autonomous Integrity Monitoring. This is extremely important for using GPS safely in aviation. RAIM is the GPS receiver's built-in capability to check the health or integrity of the satellite signals it's receiving.
Checking if the signals are trustworthy.
Exactly. Sometimes the satellite might transmit slightly inaccurate data. RAIM allows the receiver to detect such errors. To simply detect that there is an error somewhere in the received signals, the receiver typically needs to see at least 5 satellites.
And to figure out which satellite is bad.
To actually isolate the faulty satellite and exclude its data from the position calculation, the receiver usually needs 6 satellites. Some systems can achieve RAIM with fewer satellites if they also incorporate barometric altitude information from the aircraft's altimeter that's called baro aiding.
Why is RAIM so critical?
Because without RAIM capability, or if RAIM is not available due to insufficient satellite geometry, your GPS receiver could be calculating and displaying a significantly wrong position without giving you any warning. You'd have no assurance of its accuracy.
That sounds potentially dangerous.
It absolutely can be. Relying on erroneous GPS information could lead you into terrain, airspace, or just get you completely lost.
The source also mentions selective availability, SA.
Yes, SA. That was an intentional degradation of the accuracy of the civilian GPS signal that the U.S. military used to apply for security reasons. However, SA was officially turned off permanently back in the year 2000, so it's not really a factor anymore, although some older receivers might still account for it unnecessarily.
GPS sounds like an incredible asset for VFR pilots. Direct routes, great situational awareness.
It truly is. It can make navigation much easier and provide fantastic awareness of your position relative to airspace, terrain, weather, etc. However, the source is very clear in stressing some critical limitations and warnings, especially regarding VFR use, and particularly with portable or non-certified units. The biggest warning: never rely solely on GPS for navigation.
What are those key concerns specific to VFR GPS use?
Okay, number one is RAIM, as we just discussed. Many basic VFR or handheld GPS units either lack RAIM capability altogether, or they don't provide clear alerts to the pilot if RAIM fails or detects an error. This means the unit could be displaying hazardously misleading information, HMI,
Yeah.
without you knowing it. Cross-checking with other navigation methods, pilotage, dead reckoning, VORs is absolutely essential.
What else?
Database currency. This is huge. While the regulations don't strictly require the database in a VFR GPS to be current, using an outdated database, especially the moving map display, can be incredibly dangerous because airspace boundaries change, navaids are decommissioned, airport information gets updated, new obstacles appear. If your moving map is showing you old airspace boundaries from a database that's a year out of date, and you use that map to skirt around Class B airspace, you could fly right into it based on false information. The source strongly advises, if your database isn't current, disregard the moving map for critical navigation decisions, especially regarding airspace. Verify waypoints against current charts.
That's a really critical safety point. Outdated map equals potentially wrong information.
Absolutely. Another point is antenna location for portable units. Often, handheld GPS antennas are just placed on the glare shields for convenience, which might not be the optimal location for consistent satellite reception. This can lead to intermittent signal loss, especially during maneuvers. Signal loss combined with a lack of RAIM means you could lose position accuracy without warning. Also, any permanent mounting of GPS antennas must comply with aircraft maintenance regulations. Part 43.
So boiling it down, what's the takeaway for using GPS safely in VFR flight?
Know your equipment. Does it have RAIM? How does it alert you? Always, always cross-check your GPS position and guidance with what you see outside, pilotage, and where your calculations say you should be, dead reckoning. And maybe tune in a VOR as backup. Keep your database current if you rely on the moving map, or be extremely cautious and verify everything against current charts if it's outdated. Be prepared for potential signal loss with handhelds. And learn how to use your specific GPS unit properly. Read the manual, practice on the ground. GPS is an amazing tool, but it's just one tool in the toolbox. The pilot is ultimately responsible for navigation.
The source also briefly mentions VFR waypoints. What are those?
These are basically supplementary reference points designed specifically for VFR navigation, often used with RNAV systems like GPS. They're added to databases and depicted on charts, usually with a 4-point star symbol or sometimes a magenta flag, if they're co-located with a charted visual checkpoint.
What's their purpose?
They help with situational awareness, especially in unfamiliar areas. They can be used to define routes, mark points for position reporting, or help pilots navigate around sensitive areas like specific airspace or special use airspace. They usually have 5-letter names, often starting with VP, like VPXYZ. If a VFR waypoint is co-located with a named visual checkpoint, like a bridge or dam, you can use the checkpoint's name when talking to ATC.
Okay, so we have all these tools, charts, calculations, VOR, NDB, GPS. But what happens if, despite everything, a pilot realizes they're genuinely lost?
It's a situation every pilot needs to be prepared for. It can be stressful, even frightening, especially if fuel is becoming a concern. The source provides some clear, logical steps. The classic 5 C's often come to mind: climb, communicate, confess, comply, conserve.
Let's break that down. First, climb.
Yes, the very first recommended action, if it's safe to do so considering clouds, icing, and other traffic, is to climb.
Why climb? What does that achieve?
Climbing does several important things. It increases your visual range. You can see further to look for landmarks. It improves your reception range for VORs and communication radios. And it makes your aircraft much more likely to be seen on ATC radar.
Okay, so climb. Then communicate and confess.
Right. Get on the radio. Try contacting any ATC facility whose frequency is shown on your chart for the Area Flight Service, FSS, approach control, center, even a local airport tower frequency if you think you're near one. Confess. Tell them you are unsure of your position. Don't be embarrassed. They are there to help.
What can they do?
They can try to spot you on radar and give you vectors, headings to fly. If they can't see you on radar, they might ask you to try transmitting on a specific frequency while they use direction finding, DF equipment, to get a bearing on your signal. In a real emergency, transmit on the universal emergency frequency 121.5 MHz and set your transponder to code 7700.
Comply.
Do what ATC tells you to do. Follow their instructions precisely.
And conserve.
Conserve fuel. Reduce power to the maximum endurance setting if fuel is critical. Fly direct routes if possible once oriented. And look outside. Try to orient yourself using landmarks. Look for town names on water towers, distinctive geological features, major highways. Use any navigation equipment you have, VOR, cross radials, GPS position, to try and pinpoint yourself on the chart.
What if you're not lost, but something forces you to change your plan mid-flight, like unexpected bad weather ahead or maybe a system malfunction? You need to divert to a different airport.
Exactly. Diversion planning and execution is a critical risk management skill. Avoiding situations like flying VFR into instrument meteorological conditions, IMC, often means making a timely decision to divert.
How do you prepare for a potential diversion?
During your pre-flight planning, you should always be looking at your charts and identifying suitable alternate airports or landing areas along or near your planned route. Know their frequencies, runway lengths, available services. Have some options in mind before you even take off.
And if you have to divert in flight, how do you handle the navigation quickly? You probably don't have time for a full replan.
No, you usually don't. Speed and decisiveness are key. Your alternate is often relatively close to your original course line. First, make the decision and pick your diversion airport. Then, use your chart to quickly approximate the magnetic course to get there.
How can you approximate the course quickly?
You could use the edge of your plotter or another straight edge to draw a rough line, then estimate the bearing using a nearby VOR compass rose printed on the chart, or maybe by comparing it to a nearby airway's known magnetic course. If the alternate has a VOR or NDB, you could tune that in and fly towards it. Try to initiate your turn towards the alternate from over a known point if possible.
But the key is?
The key message from the source is, in an emergency or rapidly deteriorating situation, devote promptly. Don't waste precious time trying to calculate the perfect heading down to the last degree. Get the aircraft turned and headed generally in the right direction first. Safety first, precision second in that moment.
Once you're established on a heading towards the alternate.
Okay, now you can refine things a bit. Note the time you started the diversion. Use your knowledge of the current winds, maybe from your pre-flight forecast or recent PRIPs, to quickly estimate a wind correction angle and a ground speed towards the alternate. Calculate a rough, new estimated time of arrival and check if you have sufficient fuel. But always prioritize flying the aircraft, safely maintain control, watch your altitude, keep scanning for traffic, consider clouds and terrain on this new route.
Okay, that covers a lot of ground, literally and figuratively. Let's try to unpack what this whole deep dive into Chapter 16 really means for you, the learner, pilot, or aviation enthusiast.
Yeah, we've really journeyed through the pilot's core navigation toolkit. We started with the maps, the different types of aeronautical charts and why they're essential. Then how to pinpoint your location using the Earth's grid, latitude and longitude, and how time zones work.
We delved into the crucial difference between true north and magnetic north, tackling variation and deviation, and that whole calculation sequence to get a compass heading.
Then, the ever-present influence of wind, how it affects your ground speed and track, requiring a wind correction angle, and the fundamental math pilots use constantly: time, speed, distance, and especially fuel calculations.
We stressed the absolute necessity of thorough pre-flight planning, gathering all available information charts, chart supplements, NOTAMs, weather, and knowing your specific aircraft's weight and balance and performance from the AFM-POH.
We walk through the practical steps of actually charting a course, picking checkpoints, selecting an altitude, calculating all those headings, times, and fuel needs, and putting it all on a flight log. Plus, the why and how of filing a VFR flight plan for safety.
And then we explored the world of radio navigation from the ground-based systems like VOR and NDB, understanding how they work and how to use instruments like the CDI, HSI, and ADF, to technologies like DME for distance and RNAV for flying direct routes.
Right up to the modern era with satellite-based GPS, recognizing its incredible power but also its critical limitations and the unwavering need for cross-checking and understanding things like RAIM and database currency.
Finally, we touched on those crucial backup procedures. What to do if you get lost, emphasizing climbing and communicating, and how to handle an in-flight diversion safely and efficiently.
Phew. It is a lot, isn't
Yeah.
it? But you can see how it all builds layer upon layer, from just looking out the window and recognizing a town to drawing a line on a chart, calculating wind drift, tuning radios, and interpreting signals from space.
Yeah, and here's what I find really interesting reflecting on all this. You see this amazing progression of technology, right? From basic visual cues to sophisticated satellite navigation offering incredible precision. Yet this deep dive hammers home that the fundamental skills haven't gone away.
Not at all.
Understanding how to read a chart, how to calculate the effects of wind, how to perform dead reckoning, how to recognize landmarks, knowing your aircraft's performance inside and out, those skills are still the absolute bedrock.
They really are. They're not just historical relics. They inform how you use the advanced technology effectively and critically. They provide the backup knowledge and techniques you need if the fancy tech fails or gives you bad information.
So what does all this mean for you listening? Maybe the most provocative thought to leave you with is this. Even with this incredible array of tools available today, from a simple plotter and paper chart to a multifunction GPS display receiving signals from satellites, the ultimate responsibility for safe and effective navigation still rests squarely on the pilot's shoulders.
It's not just about blindly following a magenta line on a screen or keeping a needle centered. It's about truly understanding the principles behind it all, integrating all the available information, visual, calculated, electronic disparity, recognizing the strengths and weaknesses of each system, and always being mentally prepared to adapt and revert to more basic methods if needed. It's about knowing where you are, where you're going, and being certain you can get there safely using every resource available, including your own brain.
So what stands out to you the most about how these different layers of navigation, from the simplest visual techniques to the most advanced satellite systems, ultimately depend on the pilot's planning, understanding, and constant vigilance?